Hey everybody, it's Mr. G. Welcome back. The next in the lecture series for electric circuits, Tech 101, we are going to be talking about parallel circuits. So in the last lecture, we did series circuits. So a series circuit when we have resistors that are connected end to end, and the resistors share the same current. So in a series circuit, we have one loop and all resistors share the same current. In a parallel circuit, we have many loops. So we have many loops. We have this loop. We have this loop. And we have this loop. So many loops for current to flow. So in a series circuit, they share the same current. When things are in parallel, they share the same voltage. So if you look, this power supply is connected across this resistor, and this resistor. So all three resistors share the same voltage. Now it doesn't mean, like I said in the last one, it's not the same value necessarily or only, it is the same voltage. So they share that voltage. So let me explain that a little bit better. In the last lecture, I talked about series circuits, and I said they share the same current. So if I had a resistor here, and I had current flowing through it, let's say 10 milliamps. So 10 milliamps through that one. Then I have another resistor somewhere else that also has 10 milliamps. Those resistors are not in series. Just because the current through them is the same value does not mean they are in series. So sharing the same current means that the electrons that are flowing through this one also flow through this one. So it's not just the same value, it's the exact same current. So if we did a series circuit like this with two resistors, the exact same electrons leave and flow through both. That's what makes that in series. When we are talking parallel, it's the same concept. So in parallel, if I took one resistor and put it like this and said, okay, there's 10 volts. And then I had another resistor. And I said, okay, that's 10 volts. Those two are not in parallel. Even though the voltage value is the same, they are not sharing the same voltage. So, in order for that to be in parallel, you need to do this. Now, both components get their voltage from the same place. Where here, it's different. So, in order for it to be in parallel, they share the same voltage supply. Okay? So that means that the value is the same, but the actual place where the voltage is coming from is the same. So, in a parallel circuit, you can have many resistors in parallel. We're going to start with just two. $1K, 2.2K. So I have two resistors, and those two resistors share the same voltage source. So therefore, those two resistors get their voltage from the same place. They are in parallel. When current leaves the power supply, this is the total current for the circuit. Then some of that current is going to flow this way. The rest of the current carries on and flows this way. Then it loops around and joins back up with this one to return to the source. So, if we looked at it, we could say that this is I1 and this is I2. So the current splits and divides, and some goes this path and some goes this path. So in a parallel circuit, you can also say that there is more than one current path. So if things are in parallel, there's more than one current path. When things are in series, there's only one current path. So now we're left with voltage. We're left with total current. We are also left with current number 1 and current number 2. So now, V total is 10 volts. That total voltage supplies a current to the whole circuit. That's what I total is. That current flows along. It gets to a point in the circuit where it sees that there's a split in the path. So Some current will go down this path, and some current will continue down the other path. How much current goes each way is what we're going to be figuring out. So think of it like this. If you have a river flowing, so we've got a flow of water in a river, then the river branches off. Some water will go this way, some water will go this way. Now, how much of the total water will go this way depends on the actual width of that part of the river. So the width of the path is the restriction for current. So less restriction, more of the current goes that way. More of a restriction, less of that water goes that way. So think about it when we're talking about current. Okay? Water, current. So think about it the same way. If this was the total current, and the total current was coming out of the source, it reaches a split in the road. Depending on the resistance of each path will help to determine how much of the current goes one way and how much of the current goes the other way. If the resistance in this path is larger than the resistance in this path, then this one gets more current, this one gets less current. And what is that based on? Well, everything comes back to our Ohm's law. So if we looked at this as current 1 and this as current 2, we can conclude that if all of the water is coming down this part, and some of it goes this way, and some of it goes this way, we can conclude that if you take the water in I1 plus the water in I2, you would get the total water. So the total current flowing is split. Some of it's going here, some of it's going here. But if you added up the amount of current in this branch and in this branch, they're going to come up to the total. If we added another branch, and we called it I3, and some of the water went down there, then I3. This rule is known as Kirchhoff's current law for parallel circuits. In our last discussion, we had Kirchhoff's voltage law for series circuits. Kirchhoff's voltage law for series circuits states that if you add up all of the individual voltage drops, they add up to the total. Kirchhoff's current law for a parallel circuit states if you add up all of the individual branch currents, they must equal the total. So if we go back to our real life example, I total is actually equal to I1 plus I2. So if the total current leaves the source, it will split I1, I2. Let's go back to this example with the water. So what happens if I have water here? This represents I total. Then I have a split. This is I1. This is I2. What happens if somewhere down the river these two things merge again? How much water is flowing here? Well, we got I total, it splits, and then that water comes back together. So the value that's over here is the same as I total. So when the branches split and rejoin, all of the water from here gets back added to all the water from here, and it becomes the same as what I total was, or the total water in the beginning. The same thing happens here. So this current comes and rejoins back with this current and flow together back to the source. So the value of current over here is the same, I total, as it was here. So when the current leaves, splits, rejoins, and then flows back to the source and finishes the loop. Now, I1 and I2, they are based, or we can look at it and calculate it based on Ohm's law. We have 10 volts across this resistor. We have 10 volts across this resistor. Ohm's law tells us that if we have a voltage, so 10 volts, divided by the resistance 2.2K, we would get a current. Same thing here. Voltage across that resistor, 10 volts divided by 1K. So if we brought out the trusty calculator, and we can say 10 volts divided by 2.2K equals 4.5 milliamps. .5 milliamps. Then we do 10 divided by 1K, 10 milliamps. So if we know I1 based on Ohm's law is 4.5 milliamps, I2 is based on Ohm's law is 10 milliamps, then I total is adding those two up. So that comes to 14.5 milliamps. So, in this particular circuit, I total leaving the source is 14.5 milliamps. When it splits, I1 that flows through this resistor is 4.5 milliamps. I2 that flows through this resistor is 10 milliamps. Then they rejoin and flow back to the source. So, we know from last week's lecture that we have voltage totals in a circuit. In this case, the voltage total was 10 volts. We also have I total in a circuit, which in this case is 14.5 milliamps. We also know our individual values of resistor. But yet, we do not know what the resistance is of the total circuit together. So our total of the full circuit, well, we know what Ohm's law is. Ohm's law tells us R total is equal to V total divided by I total. So when we're dealing with full circuits, Ohm's law, total gives us total. So that's 10 volts divided by 14.5 milliamps. And we'll grab our trusty calculator again. 10 volts divided by 14.5 milliamps equals, we'll round that off to 690 ohms. So the total resistance of that circuit calculated is 690 ohms. The total current of that circuit is 14.5 milliamps. The total voltage is 10 volts. We have one battery supply and it supplies everything. So, using Ohm's law, we can actually solve for all of the things inside a parallel circuit. So voltage, current totals, current individuals, and the total resistance of the full circuit. So, if you notice, 690 ohms. It's a little bit different. We have 1,000 ohms here and 2,200 ohms here. So how is the resistance value lower than these two? Well, let's take a look. Alright, so I'm going to introduce you to a new term called conductance. So, conductance, when something is conducting electricity, so allowing current to flow, it says that it has conductance. So how does that compare to resistance? Well, conductance is the ability to allow current to flow. So conductance lets current flow. Resistance tries to hold current back. So resistance tries to stop current from flowing. So they're the opposite. Complete opposite. So resistance was measured in ohms. Conductance is the opposite of resistance. It's actually the complete reciprocal. So conductance has the symbol is G. Resistance is the complete opposite of conductance. So it's the reciprocal. One tries to stop current from flowing, one tries to let current flow. So resistance is actually 1 over G, or conductance is 1 over R. So they are the complete reciprocal of each other. One tries to let the current flow, the other one tries to stop it. So conductance, since it's the exact opposite, used to be called, the unit used to be called the mho. It's ohms spelt backwards. But in recent years, the unit has morphed into Siemens. So the symbol for conductance is G, and the current unit is the Siemens. To calculate it, it is the complete opposite, the reciprocal of resistance. So you could say that R is 1 over G, or G is equal to 1 over R. They are the exact opposite of each other. So something called conductance. So how does that have anything to do with what we're talking about? Well, if I have a power supply, and I have one resistor connected to that power supply, this circuit has a certain total resistance. But, as we learned, since current doesn't stop completely, it does allow some current to go. So therefore, even though it has some resistance, it must also have some conductance. So, if we looked at this, the total conductance of that circuit is going to be equal to 1 over R. So by having one resistor there, it resists some current flow, but therefore it also allows some current to flow. So the resistance is a way of representing holding the current back a little. Conductance is a way of representing letting some current go through. So now I have one resistor, therefore my conductance is equal to 1 over that resistor. What if I provided another path for current here? Resistor 2. Does anything change with the amount of current that's flowing through R1? No, because the current through R1 is based on Ohm's law. 10 volts divided by R1. Doesn't matter if R2 is there or not. So we would have a certain total current, I total. Then we add this next branch. what happens to I total? Well, I total has to increase because now we have current flowing down that branch. What happens if we throw another branch? Well, I total must increase again because we have another branch. So, we have a certain conductance with one branch. We are now conducting more from the supply because we added another branch. We are now conducting more from the supply because we have another branch, etc., etc., etc. So if we looked at the total conductance of this circuit, it would be relationship to the conductance that is R1. So the conductance down that first branch plus the conductance down the second branch plus the conductance down the third branch, etc., etc., etc. So every branch we add adds conductance to our circuit. It adds another possibility for current to go. So every branch we add adds another set of places for the current to go. So we're able to conduct more. So as a quick example, I have 3 resistors here. There's nothing here. I have 3 resistors here. Is there any other place for current to go? No. It has to go through those resistors. But if I now added a 4th resistor, there is an extra place for current to go, an extra path. So therefore, extra conductance. So, if we know this, and we know this, we can actually combine those two things, and we can say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. So when we have resistors in parallel, we can actually calculate the total resistance using 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. This is the generic formula for calculating the total resistance in a parallel circuit. Now, we just do a little bit of math arranging, and this works out to be solving for R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. So this is the overall grand formula for calculating the total resistance in a parallel circuit. All right, so let's apply this to our previous question. So, remember we had done things via Ohm's law, and we came out with 690 ohms using Ohm's law. Now what we're going to do is we're going to use this formula to calculate our total resistance in this circuit, just to see what we get as far as difference. So here's the formula. In our case, we're going to say that our total is equal to 1 over 1K plus 1 over 2.2K. And see what that actually gets us. If everything works so nicely, it should give us an answer that's close to 690 ohms. Again, based on rounding off and so forth, let's just see. So we've got 1,000 ohms, 1 over, plus 2,200 ohms, 1 over, equals 1 over. I get 687.5 ohms. So 687.5. So 687.5 ohms. So this is a calculation way, and then this is utilizing what we had. So remember, we had some rounding off errors. So every time we do mathematics and we round off and then use that number in another calculation and round off, every time we are magnifying the error. So calculating wise, directly our total is 687.5. Using this method and Ohm's law, we came up with 690 ohms. So that is close enough. So this formula for calculating our total works for each and every case of a parallel circuit. So if we have 10 resistors in parallel, we use this formula, and it will be 1 over R1, 1 over R2, 1 over R3, etc., 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 all the way up to 1 over R10. So this is the master formula for calculating our total in a parallel circuit. Now, there are some shortcut formulas. Let me show you what they are. There are two shortcut formulas for calculating our total. So I'm going to put them all here. So here is our total. Here's the master formula. 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. This case will work, or this formula will work in any parallel circuit. So this will work in all cases. If there are only 2 resistors, if there are 2 resistors in parallel, we can use this formula. Our total is equal to R1 times R2 divided by R1 plus R2, otherwise known as product over sum. So this formula works if we have only 2 resistors. So let's go back. Here's our question again. Let's use the shortcut formula for our total. Product over sum. So that is 1 K times 2.2K divided by 1K plus 2.2K. So we got 1,000 times 2.2 thousand divided by 3.2 thousand equals 687.5. Exactly the same as this. So 687.5 ohms. Exactly the same. So this formula can be used in all cases. This one can be used if you have two resistors. So two resistors in parallel. And then we have the last one, our total. This one is used if you have any number of resistors, all of the same value. So let's pretend you had a circuit that looks like this. All resistors in parallel, all of the same value. So in this case, I've got 1, 2, 3, 4, 5 resistors, all of the same value. So if I did the whole R total is 1 over 1K plus 1 over 1K plus 1 over 1K plus 1 over 1K plus 1 over 1K. We know that that formula works in all circumstances. So we have 1, 2, 3, 4, 5 resistors. There we go, 5 resistors, each of them the same value. If I did it this way, it would be 1,000, 1 over plus 1,000, 1 over plus 1,000, 1 over plus 1,000, 1 over plus 1,000, 1 over equals 1 over. 200 ohms. The shortcut formula is to actually take the value of one resistor and divide it by the number of resistors you have. So in this case, 1K divided by 5 equals 200. So, shortcut formula. Any number of resistors as long as they're of the same value. Our total is you take the value of one resistor and you divide it by the number of resistors in parallel. There are the three formulas that are used to calculate the total resistance in any parallel circuit. This one works in all cases. This one is a shortcut that works when you have only two resistors in parallel. This one works when you have any number of resistors in parallel, but they all have the same value. So the three formulas for calculating the total resistance in any parallel circuit. So again, this one works in all circumstances. This one works when we have two resistors in parallel. This one works when we have any number of resistors in parallel, but they all must have the same value. Okay, so let's put this all into a real life example. So I grabbed 3 resistors from my kit and my breadboard. And what we're going to do is we're going to build this parallel circuit. So the resistors that I grabbed, the first one, the colors brown, gray, orange. So brown, gray, orange is going to be 18 kilo ohms. So basically what I'm going to do is I'm going to build my circuit like this. Like that. So there's 18 kilo ohms. The next one I grabbed, brown, black, orange. That's 10 kilo ohms. I will put that one in there. And then the next one, orange, orange, orange. So that makes this one 33 kilo ohms. So now I have to make the connections, because my board right now, those resistors do not have a parallel connection. There's no connection in my board underneath to go from here to here, here to here to here to here. So I'm just going to do that with some wire. So I have to connect this resistor to this one. I will connect this side to this side. I will connect this point to this point. And I will connect one more wire, please. There we go. I will connect this point to this point. So just to get rid of the black, make everything look uniform. There. So now all 3 of those resistors are connected in parallel. We've got 18K, 10K, 33. So now I'm going to apply my voltage. So I've got 10 volts, and I'm going to apply my 10 volts to that circuit. So the 10 volts getting fed to all 3 of those resistors. So I'm going to slide this over here for a second. What we want to do is we want to mathematically solve this circuit first, and then we will perform the measurements and prove that our answers are correct. So, to solve this circuit, we need to be able to figure out I total, I1, I2, I3. We know that the voltage across all of those resistors is going to be 10 volts. That's a given. We know the individual values of resistors, but what we don't know is our total. So all the things that we don't know for this circuit, I'm going to put on this side. All the things we do know, I'm going to put on this side. So we do know that the voltage total is equal to 10 volts. We know that the voltage across R1 is equal to 10 volts. Why do we know that? Because they're in parallel. They share the same voltage. Voltage across R2 is 10 volts. Voltage across R3 is 10 volts. We know R1 is 18K. We know that R2 is 10K. And we know that R3 is 33K. We know that from the colors. What we don't know is our total. We do not know I total. We do not know I1, I2, or I3. There are many ways to solve this. The first way I am going to solve this is the way we solved the other one, working through Ohm's law and Kirchhoff's current law. So, Ohm's law tells us that I1 is equal to VR1 divided by R1. So VR1 is 10 volts, R1 is 18K. So we have 10 divided by 18K. We have 0.55 milliamps. So we'll say 6, so 0.56 milliamps. I2, we know that the voltage across R2 is equal to 10 volts. And we know that R2 is 10 kiloohms. So 10 volts divided by 10 kiloohms. 10 volts divided by 10 kiloohms. We have 1 milliamp. The next one, we have VR3 divided by R3. Again, VR3 is 10 volts, R3 is 33 kiloohms. So, VR3, 10 volts divided by 33 kiloohms, 0.3 milliamps. Kirchhoff's current law So we solved these ones using Ohm's law. I total, we're going to use Kirchhoff's current law. Kirchhoff's current law says that if we add up all of the individual currents, we will get to the total. So that is I1 plus I2 plus I3 equals 1 plus 0.56 plus point. So that becomes 1.86 milliamps. So I'm just doing that in my head. 1 plus 0.56 plus 0.3, so 1.86 milliamps. Our total, we're going to use Ohm's law again. So with Ohm's law, it states that R total is equal to V total over I total. We use totals to calculate totals. V total is 10 volts. 10 volts. I total from this calculation is 1.86 milliamps. So therefore, R total is going to be 10 divided by 1.86 exponent 3 to the negative equals 5.38 K. So 5.38 kilo ohms. So now we have solved for everything that we need to know about this circuit. We needed to know the total current, got it. We needed to know the individual currents, got it. We needed to know the total resistance of the circuit, got it. Could we have done it another way? Yes, we could. So, one of the nice things about being able to solve circuits and knowing the rules is that we can check our answers. So what I'm going to do is I'm going to slide this over here and hopefully that stays on the screen enough. Good. Let's check our answers. We know that our total we can calculate using Ohm's law. But we also know that we can calculate our total using one of these rules. So when we look at this, do we have 2 resistors? No, we have 3. Do we have any resistors that share the same value? No, they are all different. So the only formula that works is this top one. So 1 over 18K plus 1 over 10K plus 1 over 33K. If we plug that all into the calculator, it should come up with a value very close to 5.38K. Again, rounding off because of calculations. So we've got 18K 1 over plus 10K 1 over plus 33K. Now, on my calculator, this is how it's done. On your calculator, it could be different. So again, you must get used to using your calculator. 5.38K. 5.38K. 5.38 kiloohms. So if I did my calculations this way and I came up with that answer, then I double checked my calculations and came up with this answer, then we have a very good assumption that those two are correct. So now we know this. We can say that I total is equal to V total over R total. We know that V total was 10 volts. We know that we've just calculated our total at 5.38 kiloohms. 38 kiloohms. So we can now calculate I total. And we can say that 10 divided by 5.38, 1.86 milliamps. 1.86 milliamps. So now we have proven that this calculation and this calculation match. We can prove that this calculation, where we added up the individual currents, remember, we added up the individual currents and we got this. We can prove that this now matches this. So we have checked our answers. We got this from adding these. So if we got this from doing this, then these answers are most likely correct as well. So when you're solving for circuits like this, there are ways to mathematically check your answers. So now that we've got this done, we've got the circuit built, let's perform some measurements and see if we can actually prove this to be true. Okay, here we go. So here is our circuit. And what we're going to try and prove is our calculations. So here we go. So I got a multimeter. I am going to measure my currents. So we're going to set this up to measure currents. So we're going to break the circuit, put the ammeter in place. So now what I'm doing right here, I am measuring the total current, 1.83 milliamps. So our calculation, we got 1.86. So with our calculation error and our measurement error, that is well within what we would figure to get. So this is where I would measure I total. So that would be right here, down this wire. So I break the circuit here, put the ammeter in, and I am measuring I total. So now what I'm going to do is I'm going to measure I1, I2, and I3. So I got to break it right here. Okay, so the first one, I broke the circuit here, put the ammeter in. Now I'm going to break it here, then here, then here. So let's take a look. So I put the circuit back together. So there's the circuit back together. Now I'm going to identify this point. So that point is right here. So let's pretend I was going to cut that wire. So let's pretend, snap, I just broke that wire right there like that. Okay, so now what I want to do, oops, sorry, this got to go here. I just snap that wire. So now what I'm going to do is I need to close up that gap with the ammeter. And I need to put my Power supply back. Just move it out of the way so it's out of my way. There we go. So what I've done is I've just taken it as I pretend I broke this wire. Boom, I just broke that wire and I put the amp meter on one side, closed up, and here's my current, 0.51, 0.52 milliamps right there. So I'm going to now put that resistor back in its place. I am going to go to the next resistor. And again, I'm going to do the same thing. So snap, I just broke that resistor. So let's pretend right there, that's where I broke my wire. I will put my amp meter in place. 0.97, 0.96, pretty close to 1 milliamp. So now I will put that resistor back into place. Now the last one, again, we're gonna snap, there we go. .2627 is pretty close to 0.3. Again, with the inaccuracy of my meter and so forth, okay, these values are all coming up very, very close to what you would calculate to be. So now I'm going to go back. And I'm going to put this in here, and there I've got my circuit back in place. Now, got to remember that all of these values were calculated based on perfect resistors. Remember, each of those resistors have a tolerance. They could be out by up to, and I think they're all gold, so they could be out by 5%. So that could account for a little bit of our error. We had calculated our total to be 5.38 kiloohms. So what I'm going to do now is I'm going to measure our total. So our total would be from the supply looking that way. So I take out the supply and I'm going to measure the total resistance of that circuit. So you cannot measure resistance with the supply connected, so I must remove the supply. So I'm just going to put this wire here where the supply was connected to make things easy for me. So these two wires represent where the supply was. So now I'm going to measure my resistance. So the supply has been removed. I am now going to connect here and measure the total resistance of that circuit, 5.29 kiloohms. We had calculated 5.38. Remember, each of these resistors has a 5% tolerance. So that means the value can be off by 5%. So 5.3 is pretty close to 5.38. It's well within tolerances. So what I've done is I have just proven by measurement that all of our calculated values, so all of our calculated values, our total, I total, and the individual currents are all the same as what we calculated and what we measured. So I measured and calculated and measured and calculated, and everything is the same within tolerance. Again, remember, these values can be off by 5%. So if they are, expect these values and your measurements to be off by up to 5%. So what we've got so far is being able to solve a parallel circuit. So I'm just going to take this and put it over here for a moment. One thing that I want to show you are total. When you are looking at measuring or calculating R total, look at this. Here is R total. R total was from 33K, 10K, 18K. So whether we did it Ohm's law method or we did it using the formula method, the value here came out to be the same, right? 5.38. In a parallel circuit, R total of a parallel circuit must be less than the smallest resistor in the network. And that's in that parallel network. When you calculate R total of a parallel circuit, the resistance must be less than the smallest resistor. Okay? So it must be less than the smallest resistor in that network. If we looked at all the cases that we've done, that would be true. That is because if we go back to this, with every resistor we add, the conductance goes up. So therefore, the resistance must go down. So with every resistor we add, the conductance goes up. And since conductance is the complete opposite of resistance, so since the conductance increases, the circuit has the ability to conduct more. The resistance must fall. So the total resistance must go down. So if conductance goes up, resistance must go down. So therefore, when you are calculating R total, the total resistance of the circuit must always be less than the smallest individual resistance in the network. Smallest resistance here is 10K. Our R total was 5.38K. If I took $2K, $4K, $1K, all in parallel. From this rule, I must be able to calculate an R total that is less than 1K. 1K is the smallest resistor in that network, so the R total must be less than 1K. When we looked at series circuits, every resistor you add in series increases the resistance of current flow. In a parallel circuit, every resistance you add actually provides another path for current that wasn't there before. So therefore, the conductance of that circuit goes up. And when the conductance goes up, the resistance falls. So, with every resistor you add, the R total goes down. So, a rule of thumb is R total of a parallel circuit must be less than the smallest individual resistor in that network. Alright, so the things that we covered today, you can find them in our textbook, Principles of Electric Circuits, Conventional Current Flow, Floyd and Buckla, 10th edition. We're looking at Chapter 6 in Parallel Circuits. So 6-1, 6-2, 6-3, 6-4, and 6-5 are what was covered today. So again, you can find the material in our textbook for extra reading. So until we meet again next time, I hope this helps. Everybody stay safe. Take care.